to not being late after that. So welcome everyone. I'm delighted to host you for this second lecture in this series of conferences of the Executive Master in Digital Twins for Infrastructures and Cities. I am Mathieu Arquet, the director of the Master. And today I'm pleased to host Francesca Briganti. That's how it is spelled? Yeah, great.
Perfect.
I did some Italian back school. And today, donc, Francesca, you have a PhD and you are a civil engineer and expert in structural health monitoring. And you work at N Plus company in Italy.
Yes.
And we are delighted to have you today. Though for your information, you have some students for the Executive Master live with us today and also public, open public. And inside the Master, we also have a specific course of structural health monitoring. And we are very happy to have your insight in the Italy with an Italian feedback and insight of structural health monitoring, because we know that's more and more demanding now, and the demand of sensoring and monitoring is increasing a lot. So as always, for this kind of conference, you have around 40 minutes maximum of speech. And then we will have a question and answer session at the end. Feel free to write your question in the chat if you want, and we will answer all of them at the end of the talk to not disturb the lecturer. So Francesca, welcome. Thank you again for joining us, and the floor is yours.
Thank you very much, Professor, for your introduction. Thank you also for the opportunity to speak at this Executive Master. It is both a pleasure and an honor being here today. Today, I will present to you the advanced structural health monitoring for bridges, and in particular, the Italian predictive maintenance approach. I will start by telling you why structural health monitoring is so critical nowadays, to then switch what is actually structural health monitoring, giving some basics on the monitoring methodologies and the threshold definitions. Then I will switch to the actual Italian panorama on structural health monitoring and Italy's best practice, and I will conclude with some case studies. So first of all, why structural health monitoring? Well, we all know that infrastructures all over the world are getting more and more critical due to aging, due to climate change, and also traffic growth. Plus, there is a big lack of investment for the maintenance of these kind of structures. The more stringent requirements on the infrastructure owners are leading to some investments in this kind of technology, because all the, let's say, dimension encompassed into the asset management is enhanced through this digital enablement. This is due to the fact that planning network intervention via structural health monitoring allows to do two main things. First of all, maintain only when and where needed, and secondly, maintain efficiently without the need of service interruptions. In particular, in fact, structural health monitoring solution enhance cost-effective decision-making by giving the total control over the network with real digital twin of the infrastructure stock, and create an immediate overview of the network maintenance for predictive maintenance support. It also allows for the identification of the optimal mix of intervention with a great planning accuracy, and it improves the risk management processes and also the ESG, environmental, social, and global scores of companies. They eventually lead to the reduction of potential liabilities for executive and also for non-executives. Structural health monitoring, therefore, comes as the, let's say, crossing point of some global macro trends. On one hand, we have the aging of infrastructures and the uncertainty related to the structure, the traffic growth, and the climate changes. On the other hand, we have IoT technology with new generation sensors and edge computing, and the data lakes that are enabling the implementation of big data analytics and artificial intelligence algorithms. These allow to the creation of real digital twin of infrastructures through some certified data, thanks to the implementation of blockchains and smart contracts. So this kind of certified data allow for an actual rating for the quality of the assets for the investment and population, and they allowed for the improvement through the social responsibility and the ethical investments of the companies. But what is actually structural health monitoring? We have several definitions of structural health monitoring, but the most on point one, I think, that is that structural health monitoring is a process that involves structural studies and technology aimed to a deeper and permanent knowledge of the structural state of an artifact. In fact, structural health monitoring is not just about the technology, the hardware, but it's the combination of three main sectors: hardware, software, and engineering services. In fact, we include the engineering services through a knowledge of the structures, through inspections, bridge system management system implementation, structural health assessment, FEM modeling, as well as digital twins, and the definition of structural health monitoring parameters. Then there is the actual deployment of the technology with the installation of permanent measuring systems, permanent data acquisition, data analytics, and the historical repository of the structural health monitoring parameters. And then, thanks to the software, we have the diagnostic through a constant reading of these structural health monitoring parameters. There are some guidelines related to structural health monitoring, in particular the guidelines from 2019, guidelines for monitoring and maintenance of highway viaducts, that states that the structural health monitoring can be defined in two different ways. Through the permanent measurement and acquisition system, which is a complex of devices installed on field aimed at the acquisition and measurement of the quantities, and the data analytics system. The software that permanently analyzes the data coming from the measurement system uses specific algorithm. Therefore, a monitoring system itself is basically the combination of these two aspects. What we can say is that structural health monitoring can be defined differently from what we call the traditional monitoring, that is essentially based on data collection and manual analysis. It is a kind of active or IoT monitoring that implements a series of continuous and automatic analysis in the absence of human intervention. In Italy, there is a circular that was released in 2022 that also states that there are two different kinds of monitoring methodologies, the data-driven one and the model-based one. The data-driven, or better, statistic monitoring is a kind of predictive monitoring exclusively based on data. It requires only information of instrumental nature filtered by essential data analytics, and it provides a first level of alert in case of statistic anomaly. The model-based monitoring is a method that is based on the matching of the data coming from the field systems and digital twin models. And it provides information from a combined use of this data and these mathematical models. This actually aims at a real digital twin of the artifact with the behavior at the damage condition. Another thing that is important to understand is that both these two methodologies are based on structural health monitoring parameters and not on raw data. Raw data are the data that are automatically generated from a permanent measurement system that are not filtered, not processed in any way. These data are often very large and do not give much information if they're not processed. So the structural health monitoring parameters comes in hand. These parameters are the raw data processed through some specific algorithms, which can be, for example, statistical algorithm or more advanced ones like operational model analysis. They are basically synthetic parameters which are relevant to identify a physical phenomenon which is tracked over the monitoring lifetime of the bridge. To give you some basics on the monitoring methodologies and threshold definitions, I will start with telling you how we can get to our strata health monitoring parameters. The very first thing to do is a proper system design. In fact, it is crucial to underline the importance of the preliminary design of the monitoring system because we need to actually understand the probable or ongoing degradation phenomena. These allow us to identify the actual parameters that need to be monitored. Then these parameters must be monitored in time and are useful to identify certain structural behaviors or define degradation phenomena. So these parameters need to be extracted by the raw data that I acquire from the field systems that must be processed in order to obtain useful information. So basically, statistic functions or algorithms are applied on determined time frames, typically on an hour base or for long-term monitoring, or shorter time frames for event-based monitored, in order to derive the structural health monitoring parameters from the raw data. To give you some examples for dynamic data, the structural health monitoring parameters are usually extracted from the application of operational model analysis algorithm, whereas for static data, they are mainly extracted with the application of statistic functions. For example, we can derive the maximum, the minimum of, or the average of some data. Then what it is also very important for both the static and dynamic data is to mitigate them from the thermal effect. In fact, the structural health monitoring parameters must be calculated after the application of the mitigation of the thermal effect algorithm in order to make possible the comparison of two parameters registered in different environmental situations as well as in different times of the days. The data-driven and the model-based methods, therefore, are both based on the structural health monitoring parameters, and they are useful usually for two different things. Let's say that the data-driven method uses the structural health monitoring parameters mainly to detect damage or anomalies in time. So let's say in a kind of a slow time frame. So they detect little changes in the structure that are difficult to detect by eyes because they have been going on for some time. Whereas the model-based method comes with the fusion with some finite element methods, and therefore they are useful to simulate the structural state of the artifact, and therefore to make future scenarios or to see whether after an event the immediate response of the structure is different from the one expected from the design model. In the data-driven method, the structural health monitoring parameters are usually monitored by creating control charts. Through these control charts, what we can do is to trace the standard behavior of an artifact to the application of statistic regularity model. And we trace the structural drifts or other relevant phenomenon. In this kind of monitoring, it is possible to set some thresholds to receive alarms with two different methodologies. The first is by calculating the occurrences. So, for example, it is possible to set a minimum or a maximum threshold on any parameters by calculating the levels at which we are grouping the 98% of the occurrences, for example. And if this threshold is exceeded for a certain amount of time, that means that the structure has significantly changed its behavior and therefore a damage occurred. Another way is by performing a load test. So for static data especially, a load test can give many interesting information. For example, it is possible to relate a certain unknown load state to a certain bending of the structure. And therefore, we are able to set a threshold where we do not want the structure to bend at that specific level. In the digital twinning or model-based methods, the threshold settings is quite different. In fact, in this case, what we need to do is that we need to calibrate an existing finite element model, with the data coming from the field. So, for example, we register some data and we see that the behavior on field doesn't match the one expected by the design model. What we do, therefore, is that we go and we change some parameters in the original model, for example, the stiffness of certain elements, and we try to go and match the two behaviors. Once we succeed, what we have is a digital twin of the structure that reproduce perfectly the behavior on field. And therefore, now we don't have a design model, but a model of the damage condition. Here, for example, you are seeing an example of two different models. One is a FEM simulation, so the design model, and the other one is the model coming from the on-field data. As you can see, we were able to match perfectly the frequencies coming from the FEM simulation to the ones on detected on data and therefore of the damaged condition. You can see how the frequencies matches at different modes of the structures, and therefore we were perfectly able to reproduce the damaged condition. I will now switch to the actual Italian panorama on structural health monitoring technology. And this is because Italy was the first country to apply this kind of technology on a national scale. In fact, what happened in Italy was that there was a tragic collapse, the collapse of the Morandi Bridge. Probably many of you have already heard of this tragic collapse where 43 people passed away. This wasn't the very first bridge collapse in Italy. It was actually the 11th since 2013. But in some ways, it was the one that struck the hardest, the largest highway operator at the time, which was Autostrade per l'Italia, and created a very big public pressure of people asking to the government for a smarter way to manage infrastructure. And this is really where the government had to react, and it did so with a project entailed in three phases. First of all, there was a creation of the new guidelines for classification and management of risk, safety assessment, and monitoring of existing bridges. Then there was the establishment of the project Strade Sicure 4.0, which means Safe Roads 4.0, for the implementation of dynamic monitoring systems for the remote control of bridges and viaducts. And finally, there was a very big investment plan of over 10,000 million of euros for infrastructure maintenance in the 2021-2026 period. Starting from the new guidelines, what we as a nation realized is that we couldn't carry on with our original way of assessing the infrastructures. In fact, until the collapse of the Morandi Bridge, we used to assess the infrastructure like any other country in the world. So we had a census and then we proceeded with visual inspections. If any major defect was detected, we needed to redo the calculations on the structure as per our original code. But now the situation was that we had operators managing thousands and thousands of infrastructures, all of which were approaching their design service life. So it wasn't feasible to conduct thorough verification of all of them at the same time anymore. We needed to create some kind of order of priority among these structures. So what we did was that we introduced an intermediate level, the level of the class of attention, which calculated the risk connected to the infrastructures with regards to four parameters: structural, seismic, landslide, and hydraulic. The combination of these four risks created a ranking in 5 classes: high, medium, medium low, and low. All the structures falling in the high-risk classes, so high and medium high, were compelled to install a permanent monitoring system on them. To give you a brief idea of the numbers I'm talking about, in this map, you are actually looking at the structures in high and medium high risk classes for a single Italian highway operator, ANAS. We are talking of about nearly 1,000 structures. And of course, there were a huge investment plan for the instrumentation of all of these structures. In particular, we have a funding of 450 million of euros from the Next Generation EU funds. The funds were intended for a first phase, which was the integrated census, classification, and risk management system for 12,000 segments. The instrumentation of 6,500 segments, and finally the implementation of a BIM model for 200 structures. From these, we have derives great Italy's best practice in investment for structural health monitoring technologies. And in particular, we understood that to create this kind of investment plan, the project needed to entail several phases, not just the one of the instrumentation. But we needed, first of all, to do massive inspections and implement bridge management system softwares. We needed to conduct some structural assessments on these structures. Then there came the deployment of the structural health monitoring permanent measurement system. And with the digitalization of the infrastructures, also through FEM and digital twin models. Finally, there was the phase of the transitability grade assessments, as well as the one of the risk rating with periodic reports and predictive maintenance support systems. The phase of the inventory and classification and risk assessment was concluded in 2024. And we are now at the phase of the instrumentation, which is also nearly concluded. It should be concluded by the end of 2026. In particular, in order to do all of these phases, the Italian government allocated 1.6 billion of euros of the Next Generation Fund plan into structural health monitoring investments. And it is expected that in Italy, the structural health monitoring investments will exceed the 5 billion over the next 10 years. As I said before, 450 million of euros of these 1.6 billions were especially allocated for the instrumentations of the bridges. ANAS, the largest Italian operator, for example, tendered over 280 million of euros in structural health monitoring technology. Strada dei Parchi, which is another operator, tendered over 230 million of euros. And other highway operators have 170 million of PNNR funding and are proceeding with several deployments. So The program main objectives in this fund plan are to create an actually integrated inventory and classification risk assessment, which is not only on an operator base, because before the Morandi Bridge, each and every operator used to do census and visual inspection based on their own criteria. So we weren't harmonized among the entire nation. But for the first time, we created, let's say, a national database where all the operators needed to adhere to certain standards. Then all the most risky structures that were evaluated not anymore according to subjective standards, but national objective standards, were compelled to install this kind of monitoring technology. And finally, the final objective was to come up also with the BIM and digital twin modeling for the most critical structures of the national network. So the investments were especially dedicated to inspection and engineering knowledge of the structures, of course, structural health monitoring system design and modeling of structures, to the supply and installation of structural health monitoring system, and to the creation of ICT platform for device management, data analytics, diagnostic, and bridge management systems. So we can say that the Italian case study created for the first time a national-wide case study that wasn't just related on a single structure, but on a national network, where we saw that starting from a situation where we were seeing our infrastructure getting older, we had an increase in the traffic growth, and also the probability of structural default increasing, we were able to implement an approach that was entailed into the inspection, the bridge management system software, and the permanent measuring system, which led to eventually the reduction of liabilities connected to owning the infrastructure, the optimization of the capital expenditure on these structures, as well as the reduction of service interruption for invasive testing. All of these created a very fast decision tool, which was capable of rating the infrastructures of the nation, which eventually also led to the reduction of insurance costs. I would like now to present some case studies of the application of this kind of technology, just to make clear what we actually can do through the implementation of these systems. First of all, I would like to go through the project rollout. So what we usually do when we go and we install a permanent measurement systems in the structures. First of all, what we do is that we conduct a massive installation on the bridges or single bridge that we need to instrument. And then we proceed in a risk assessment and cluster analysis through the use of bridge management system software. Then we identify the most critical structures and we proceed in preliminary dynamics testing of the structure in order to be able to reconstruct some actual models. Then we identify the structural criticity through the model shapes analysis, and we choose the measures for tracking the structural anomalies. Finally, we design and install the permanent measurement system. We do 1 year of structural health monitoring services. And finally, we implement some platforms for the alarm management. In the case studies I will present, we always used M+ proprietary system. This system is a digital system designed for massive installation, which works on a wire-based. The reason why we implement a wire system is because thanks to this kind of technology, we can basically conduct any kind of monitoring, dynamic monitoring, dynamic, static, but especially the seismic one, which often requires a huge amount of data to be collected and processed let's say continuously. And therefore, if we had a wireless system, we wouldn't be able to collect this amount of data without the system running out of batteries. The other characteristic of our system is that it's a digital system. And this is because it allows for several advantages, among which a higher accuracy and a long-term stability, simplified integration with other monitoring systems, as well as an improved noise immunity. It also allows for very advanced diagnostic and remote management, as well as for a great scalability and network compatibility. In fact, if we look at this graph provided by National Instrument, we can see how digital sensor surpass analog ones in terms of remote calibration and configuration, compatibility with standard protocol, ease of adding new sensor, error detection and correction, internal signal processing, as well as accuracy of measurements, whereas they are less susceptible to electromagnetic noise, as well as signal degradation over distance. The system is based on an IT architecture which uses two different computers. A first UCL computer, which translate, let's say, the data coming from the sensor into a text or tabular form, and then a second edge computer, which pre-processes the data and sends the data to the cloud through 5G connection. Finally, these data are streamed to the Vittorio platform, the proprietary platform from N+, which works both as a bridge management system software, as well as a device management and data analytics platform. Now, the first case study I would like to present is the Montevideo Viaduct. This tractor is one of our first installations. It is located in Trento, northern of Italy, and it is a simply supported bridge mixed steel concrete. The reason why we were contacted by the client here was because the hill that you see behind the first pier in the picture was undergoing a landslide, and therefore the client was quite worried that the first pier was being affected by this landslide, and therefore he was worried that the pier was either sinking or rotating. So what we designed was a monitoring system that targeted the first two spans of the viaduct that were the one next to the affected pier. And we designed a monitoring system composed of accelerometers to detect the dynamic behavior of these two spans, since this kind of measurement is highly indicative of a global behavior of the structure. Then we install some inclinometers on the two spans next to the supposedly affected pier, because of course, if the pier is rotating or sinking, then also the two spans next to it are also rotating. And finally, displacement transducers on the joints, because what we realized was also that if the two spans were rotating one against the other, then the joint was probably stuck or at least not functioning as expected. The first data that we went into looking were the data coming from the accelerometers. And here you're looking at the output of an operational model analysis. In particular, we are at the peaking phase. Here you can see clearly the first three modes of the structure, where in the first mode, which is circle in blue, we saw three very pronounced peaks. Now, for us that have some experience, let's say, in data analytics, we know that usually we encounter this kind of pronounced peaks in two different occasions. One is when we have very high noise coming from the traffic, for example, and one is when we have continuous tractors, because continuous tractors have the first three modes very similar to each other in terms of frequency, and therefore sometimes they tend to overlap. But as I mentioned before, this tractor was a simply supported one. So we really needed to make sure that it wasn't behaving like a continuous tractor, because in that case, that meant that the joint might be actually stuck, as we feared. And therefore, we immediately went into looking into the joint displacement. Here you're looking at a 6-month period. For us, this half sinusoid, it's completely normal because in Italy we have very high temperature variation between wintertime and summertime. And in fact, you can immediately see how this half sinusoid is correlated to the temperature trend. But still, once you thermocompensate the data and you clean them from the temperature effect, you can see how the joints were perfectly fine, perfectly responding within the thresholds, and as a matter of fact, also perfectly symmetrical, in a perfectly symmetrical behavior among the two transversal extremities of the bridge. So now we had the confirmation that the joint was behaving fine, and we just needed to confirm that what we saw in the dynamic data was actually noise, because dynamic behavior is usually indicative of a global behavior, not a specific problem. So what we wanted to do is that we really wanted to make sure that what we saw over there was not due to maybe some other problem we hadn't thought about. So in order to do that, we went into looking into the last sensor we had installed on our structure, the rotation sensors. So thanks to the inclinometers, we were able to tell that at the beginning, the structure was behaving perfectly fine. We can even see the daily sinusoid due to the temperature variation between daytime and nighttime. But on October the 28th, which is circled in the left graph, something happened. The structure suddenly rotated very much. I say very much, but maybe you cannot see it from the screen. We are talking about a 3 millidegree rotation, but still well outside the standard behavior. And the alarms of the system went off. But we were contacted by the client, which told us that on that very day, they had installed a very heavy building site on the structure. And therefore, they had added a lot of load by bringing trucks, New Jersey to diverse the traffic, and so on. So what we did was monitoring the structure up until the removal of the working site, which happened in November the 7th, circle in the right graph. And after the removal of the working site, we were able to tell that the structure went back to its original behavior. Not quite, there is a slight difference, which is due to the fact that when they renewed the pavement, they didn't scratch the old one off, they just poured the new one over the old one. So they did add a little bit of load, but still, we were able to tell that not only the pier was not being affected by the landslide, but also we were able to use the working site as a kind of load test. And we were able to tell that if the structure was loaded and unloaded, it was capable of going back to its original behavior. Now, the other case study I would like to present is Casal Maggiore Bridge, our longest installation. This is a 34-span bridge where we had severe degradation due to aging and an increase in the weight of the trucks passing on the bridge. So in this case, what we installed was a weight in motion sensor, which is a sensor that actually works as a weight. So it is capable of telling the exact weight of each and every truck transiting on this strip. Coupled with some inclinometer sensors on the spans, because we wanted to correlate the vertical deflection to the actual weight of the trucks transiting. The weight in motion was also connected to a camera which took the picture of the license plate of the overweight trucks. And in this installation, we had two results. First of all, the truck drivers were receiving fines from the police, so these alone decreased the overweight passages of 40%. But also, thanks to the inclinometers, we were able to tell that just 2 out of the 34 spans were undergoing abnormal deflection under heavy loads. And this is pretty much the exact same case study as before, but the reason why I present this is because I want you to see how the design of the monitoring system is important. In fact, in this case, the owner didn't want to know which spans to renew because a full refurbishment of the bridge was due in 3 years' time. In this case, where the owner had severe degradation and an increased weight of the trucks transiting, he wanted to know whether, while he was waiting for the full refurbishment, he needed to put a load limitation on the bridge or not. So in this case, we use the dynamic sensors, accelerometers, in order to recreate a digital twin of the structure in the damaged condition. And thanks to this, we were able to do some simulation with the loads transiting on the bridge and telling whether the bridge in the damaged condition was still able to sustain the loads or not. I will conclude my presentation with the case study of Dolo Overpass. And here I present this because this is very different from the others. In fact, in this case, we do not have any degradation due to aging or no specific damage. The only problem of this structure is that it was constructed prior the most recent Italian seismic code, which was released in 2008. And the owner here didn't manage just this structure, but nearly 100 structures, 70 of which were exact twins as this one. The owner here decided to do a full proof of concept, installing dynamic and static sensors on this structure, and he wanted to monitor the behavior before the seismic renewal and after the seismic renewal, where he proceeded to renew each and every element with different techniques. So, for example, one bearing with a seismic technique, one bearing with another. And by doing so, he was able to tell which technique performed best on this kind of structure, and he was able to apply this most performing technique to the other 70 structures of its stock. I just conclude by saying that the technology applies to building as well. Today I just presented bridges, but we have several case studies also regarding structures, one of which is the Milan Cathedral, where we are using our sensors to recreate once again a model of this cathedral with the help of Polytechnic of Milan. This concludes my presentation. I hope it was interesting, and I'm ready to answer any question. Thank you.
Thank you, Francesca. It was very, very interesting. I am a civil engineer myself, and I try to work with SHM, so very interesting to see all the how do you say that, the engagement of the whole country now since the tragedy of Morandi Bridge. I think it was a big shift in the mindset of people in Italy. And okay, so for now, we still have 10, 15 minutes left for questions. So feel free to write them in chat or even like to ask directly to Francesca your questions. The first one is always the most complex one. So let's wait a little. I mean, I can start because I'm very curious. So I think you saw the shift in mind of people in Italy, but at all, my question is more like social and even at the citizen impact. Do you think like it has changed very, very different from before the tragedy of Morandi Bridge? And for instance, is it easier to have public entities paying for this kind of monitoring than before the Morandi Bridge? Because I witnessed it in France. It's very difficult to engage cities or counties or collectivities with public funding to monitor and to install this kind of technologies because they don't think it's very useful right now, and it's not their priorities. You see my point? And
Yes.
sometimes they prefer like we know, like we say, like it's better to cure than to prevent than to cure a solution. It's better to anticipate this kind of spendings. So I think we try to convince them to install monitoring because it's not, maybe it's not so expensive actually, but they don't see the return of investment very well, very quickly. They don't have the people skilled in their staff. So we don't have in France the same momentum that you have since the tragedy of Morandi Bridge. So do you see this now in Italy? Is it like easier?
Absolutely. I must say that